all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Before we proceed, I'd like to give a thumbs up to our members and kindly encourage them to subscribe to our channel and check our description boxes for various videos that we have done. I usually put a link of similar discussions on those specific description boxes. So I'd like to encourage us to kindly check them, and of course they are going to be of great importance for us in understanding the various concepts under discussion. So in this particular case, we're going to look at the significance of this wave function. And from this, of course, I'm going to rely on the input of three scientists, among others, who are going to give us a clue on what basically the present understanding of this wave function is. So therefore, I'm going to look at the input from Robert Millikan. So this is famous from the Millikan experiment, oil drop experiment, and then we're going to look at the input of Erwin Schrödinger, of course, who's famous for the Schrödinger's wave equation, and then we're going to look at the work of Max Born, and see from this specific scientist what are some of the perceptions on the concept of the wave function, which we are going to use later or heavily in this various aspects of quantum mechanics. Now, according to Robert Millikan, the wave function basically represented a mathematical quantity that could assist in computing experimental results. And of course, according to Robert Millikan, he gave a small or rather minimal relevance to this specific aspect of the wave function. And therefore, its main purpose, according to him, was just to assist in computation of experimental results. So therefore, we're going to see that basically, according to him, this specific wave function bears electrosignificancy. And of course, so this basically significancy. And of course, we're going to see that the works of all the contributions of all the perception of these other scientists are going to be creating more emphasis in contrast to the Robert Millikan's argument. And then next, we're going to see that also Erwin Schrödinger gave an input concerning this specific aspect of a wave function, whereby Schrödinger argued that this wave function basically represents the amplitude of matter waves. And we had mentioned this concept of matter waves in one of our discussions, of, especially on the concept of de Broglie's hypothesis and the Max Planck and Albert Einstein's mass-energy relationship, whereby we say that the concept of basically matter waves are going to arise due to the dual nature of matter. And of course, from this we can see that Erwin Schrödinger is trying to argue that basically the concept of a wave function represents the amplitude of matter waves. And of course, this is going to be expressed in at any point in space. And of course, later on, Erwin Schrödinger also gave this specific implication of the square of this specific wave function, which he said was the density, or the what we refer to as a particle density at a particular region in space, which he referred to as a wave packet. Now, later on, we're going to see that this aspect of a wave packet, which is a specific finite region in space, is going to have some relevancy, whereby we're going to see that according to Erwin Schrödinger, this basically represented the what we refer to as the particle. And if we try to consider the particle and its charge, the product of the particle and its charge, then therefore it's going to give us the charge density of that specific particles. So therefore, according to Erwin Schrödinger, then therefore we're going to see that it's going to arise the concept of a wave packet. But basically, then our next question is going to be the specific location of this particular wave packet in that volume in space is going to be another aspect that we need to consider. Then from the concept of Max Born, we're going to see that the present understanding of the concept of a wave function is going to arise from the contribution of Max Born, whereby according to Max Born, he argued that this specific wave function basically is not going to represent the particle density, which was an argument from Erwin Schrödinger's, of course, perception, as I've mentioned, but rather it's going to represent what we call the probability of finding a particle in that specific space. And therefore, as we have been giving it in some of our various discussions, that basically this specific concept is a probability of finding particle in space, and we're going to see that this particular particle then therefore can be described at any moment or at any point in space using this particular wave function. Now, from Max Planck, I said that the square of this specific function, of course, can be given in this specific way, whereby we're going to have the absolute value of this particular square, which he argued that this can be either real or imaginary. But in our case, we're going to consider the real scenario, since basically the particle has got to be that at that particular point in space. And therefore, if we say it's imaginary, then therefore that particle is going to be non-existence. Therefore, for us to create a condition whereby we have to find this specific particle at a specific region in space, we're going to see that we're going to create a normalization condition whereby the probability of finding this specific particle has to be maximum, whereby we're going to have the implication. I hope that we have understood the contribution of these various scientists according to their perspective on the significance of this wave function. And then therefore from Max Born, we're going to see that if the particle has to be found at a particular region in space, then we can give this specific probability in terms of the square of this wave function, which I've said we're going to give it absolute value given as such. Now, the total probability of finding this specific particle at a particular volume in space, then therefore is going to call for us to include the aspect of a volume element, whereby we're going to give it as a product over the square of this wave function and the volume elements of the three-dimensional space given as such. And this probability, the maximum probability, of course, is going to be given as 1. And this particular aspect of creating this condition or satisfying this specific requirement is said to be normalized. And of course, they're going to be given in various aspects for the 3-dimension, 2-dimension, and a single axis for the x-axis respectively. So in this case, from this normalized equation, we can represent a particle that is going to be or considered to be at a particular region in space for a particular volume element, which I've mentioned in this case, which is represented by the dx, y, and z. And I've said this is going to be the volume element in space given as such. So therefore, for us to find this probability, it's going to be represented as the integral between 0 and infinity. So this one I've given it in terms of an illustration of a one-dimension box for 0 to infinity, whereby the walls are going to have the range between 0 and infinity. And then for the infinite one-dimension well, and then for the x, the range is going to be confined between 0 and L as I've given. So in this case, for the 3-dimension, which is a volume element, we are going to have this one represented as the maximum probability for the integral between 0 and infinity for x, for y, and for z given as such. And therefore, this is going to be what we refer to as a normalized equation or representation for this specific probability. Now, if a particle is confined within the x and y plane, so we can give a normalized representation for this by considering the integral between 0 and infinity for these two specific axes for x and y. And therefore, so this is going to represent basically a function, and just put it in a more elaborate way. So we're going to have the integral of this specific absolute value of the function square given as a dx, dy, dz, and this is equivalent to 1. So for the two, the particle that is confined within the x and y plane, we're going to give this specific version of a normalized equation in terms of this specific absolute value, the square of this one given as dx, dy. This is for the dx and y plane. Of course, we can give another version of it, perhaps the x and z plane and others. So this is going to be given in a normalized equation given in that specific form. And for a particle that is confined within the x-axis, the y-axis, or the z-axis, or for that case just a single axis, then we can represent that one in terms of a normalized representation of the integral between 0 and infinity of this absolute value for the wave function, which is going to be given in terms of that. So that's the first one is a general case. The second and of course the second, the third, and the fourth ones are going to represent a normalized wave equations. which basically are going to represent the probability of finding that specific particle in a volume in space, the xy plane and the x-axis respectively. So we're going to come across these various kinds of equations, especially when we're trying to define the concept of energy values and the eigenvalues or eigenfunctions as we come across them in our various discussions which are going to follow this specific discussion. So I hope that we have understood the implication of this specific wave function. And as I said, of course, we're going to come across it in various forms as we're going to discuss ahead on some of the principles of quantum mechanics, which I've mentioned, especially on the concept of a wave or a particle in a box or a two-dimension or three-dimension space, respectively. So that is it for now. Kindly check our description boxes for various links of other videos which are similar to this, and they're going to assist us, of course, try to figure out how to find various aspects of the concept of the wave function as I've mentioned. So that is it for now, guys. Bye. God bless you. Catch us in our next video.